Hello, and welcome to our segment on elementary particles. An elementary particle is a particle that has no internal parts. In other words, it's a particle that has no other more elementary particles inside of it. We've seen two of those so far, the electron and the photon. In the last segment, scientists were reducing the 92 elements that made up all of matter down to three particles, the electron, the proton, and the neutron. In this segment, scientists went to the mountaintops and put bubble chambers up in balloons to find a vast array of new particles. We'll cover those particles in this segment. We'll also probe the proton, much like Rutherford was able to probe the atom. He found a nucleus inside. We're going to find some things inside the proton. But first, let's take a look at the particles that were found from cosmic rays. The Earth is constantly bombarded by radiation from outer space, called cosmic rays. These cosmic rays are made up mostly of high-energy protons and high-energy photons called gamma rays. Cosmic rays collide with atoms in our atmosphere, generating particle chain reactions that continue all the way down to the surface. In our first segment on the Milky Way, in the How Far Away Is It video book, we noted cosmic rays are produced in supernova, like the one that created the Crab Nebula. We also noted that rotating black holes have gamma-ray jets shooting out at their poles. It is the very high energy of the deep space cosmic rays that have the power to smash into electrons, protons, and neutrons in the atmosphere, creating a wide variety of previously unknown particles. So physicists climbed mountains and went up in balloons with their cloud chambers, hunting for new particles. Here's what radiation looks like in a cloud chamber. The atmosphere in the chamber contains a vapor of alcohol. When charged particles move through the atmosphere, they cause little droplets to form. These are the cloud tracks that we see. It works on the same principle as tracks forming behind high-flying jet aircraft. Here's what cosmic rays look like in a cloud chamber. These rays are penetrating multiple lead plates, each 13 millimeters thick. To understand these tracks, we'll start with the two charged particles we already know, the electron and the proton. Here is a photograph of a particle track in a hydrogen bubble chamber from the Brookhaven National Lab. Given the direction of the applied magnetic field, electrons will curve clockwise. This is a medium-speed electron arching through the cloud chamber. Since we know the strength of the magnetic field applied across the bubble chamber, we can calculate the particle's momentum by measuring the radius of its curvature. The straighter the path, the faster the particle is moving. Also, remember that accelerating electrons lose energy by radiating photons. This causes the electrons to slow down and their curvature to increase. At these 3 points, we see that stationary electrons in our path have been bumped into motion. These are called knock-on electrons. Because they are moving very slowly, they spiral rapidly to a stop. We see a lot of these in bubble chambers. In this bubble chamber photograph from CERN, we see a particle's track rotating counterclockwise. This indicates that it is positively charged. The particle's line is also thicker than the others. This indicates that it is a large, slow-moving particle. This is a characteristic of proton tracks. Now let's take a look at some of the new particles that sent the world of physics into never-before-seen territory. In 1932, Carl David Anderson began investigations into cosmic rays and encountered unexpected particle tracks in his cloud chamber photographs. The 6 mm thick lead plate in the chamber is designed to slow particles down. This particle came up from the bottom and is curving counterclockwise, indicating that it has a positive charge. You'll note that its curvature increases after passing through the lead plate. This curvature indicates that its mass is the same as an electron. This was the discovery of the positron. In 1928, 4 years before Anderson discovered the positron, Paul Dirac predicted the existence of antimatter and proposed that all particles had antiparticles, and that they would annihilate each other if they came into contact. The positron is the antiparticle of the electron. Here's an event in a cloud chamber that shows the creation of a pair of particles, one electron and one positron. This event was the conversion of a high-energy gamma ray that kicked an electron out of an atom and was itself converted into two particles. The gamma ray photon does not show up in the cloud chamber because it has no charge. This is an example of converting energy to matter. The energy of the gamma ray photon had to be as great as the energy embodied in the two particles. For electrons and positrons, that comes to around 1 million electron volts. In 1932, Paul Kunz discovered the muon. Using both the direction of the curvature and the thickness of the bubble track, he calculated that it was a positively charged particle that was lighter than a proton, but heavier than an electron. Later on, it was found that this was the anti-muon. Here's another look at a muon created by an event that created two visible particles. The muon displayed a new particle property that had not been seen before. It was unstable. Unlike protons and electrons, the muon would only exist for a short period of time before it decayed into other particles. On average, it lasted only 2.2 millionths of a second. Muons are light, elementary particles like the electron and the positron. These particles are called leptons, meaning light. The particle that was created at the start, along with the muon, turned out to be the long sought-after particle called the pion. In 1947, using cosmic rays at high altitudes, this particle was found. Here we see an event that kicks a proton into motion and creates a muon and a pion. Then we see the pion decay into an anti-muon that itself decays into a positron. It lasted only 26 nanoseconds. Now that is a very short life. The muon lasted almost 1,000 times longer than that. Pions are spin-zero particles with around 14/100ths of a proton's mass. Although that's small, it's a good deal more massive than the muon. Pions came in 3 flavors, one with a positive charge, one with a negative charge, called the antipion, and one with no charge at all. Also in 1947, another particle called the kaon was discovered by George Rochester and Clifford Butler. They also used cosmic rays. Here's a look at their bubble chamber picture. Just below the lead plate, in the lower right-hand quadrant, you see an inverted V that extends to the lower right. Measuring the momentum and charges, they determined that they were a pion and an antipion. Rochester and Butler concluded that this event had to be a photographic record of a novel phenomenon, the decay of a previously unknown neutral heavy particle, later called the kaon. The discovery of kaons represented the first time we deduced the existence of a particle from its decay components. One of my favorite particles is the neutrino. You'll recall from our segment on radiation that the beta rays were ejected electrons. What's happening here is that a neutron inside the nucleus of an atom is spontaneously decaying into a proton and ejecting an electron in the process. The mass of the proton plus the mass of the electron is less than the mass of the neutron. And because energy is conserved, some energy must be released to make up for the difference. From Einstein, we know that energy equals mass times the speed of light squared. So, if the lost mass is turned into energy, we can calculate the amount. Just under 1,000,000 electron volts per atom. In 1927, two physicists, C.D. Ellis and W.A. Worcester, set out to measure this energy. They used radium. When the neutron ejects an electron, the electron is emitted at a very high velocity, and the proton is recaptured by the nucleus to become polonium. Radium has a half-life of 5 days, meaning that it takes 5 days for half of any amount of radium to transform into polonium. The experiment was simple. Place the most pure form of radium available at the time into a calorimeter. A calorimeter keeps the energy of the beta radiation inside the container. Over the 5 days, ejected electrons heat the water. Measuring the change in temperature allows us to calculate the amount of energy absorbed. The results showed that each radium atom naturally emits 0.36 million electron volts. But here we had a significant discrepancy. Conservation of energy and Einstein's equations called for 0.8 million electron volts. That's more than twice as much as was measured. This was a real problem. Niels Bohr thought that the conservation of energy didn't hold in this case, while Wolfgang Pauli thought that it did and proposed that there must be another particle that doesn't interact much with its surroundings and carried away the missing energy. In 1931, Enrico Fermi named Pauli's particle the neutrino, or a small neutral particle. The neutrino's predicted mass was around 1/3 of an electron volt. This is over 1,000,000 times smaller than the electron. Its predicted spin was 1/2, and its predicted speed was almost the speed of light. This particle was finally observed in a hydrogen bubble chamber captured in 1970. The invisible neutrino enters from the lower right and strikes a proton, where the 3 particle tracks originate. The proton is kicked into motion, and the neutrino is converted into a muon and a pion by the power of the collision with the proton. The neutrino is a critical component in many nuclear reactions that occur in stars. The detection of solar neutrinos and of neutrinos from supernova 1987A marked the beginning of neutrino astronomy. Neutrinos are among the most abundant particles in the universe, 1 billion times more abundant than electrons, protons, and neutrons that make up stars, planets, and people. In 1969, a team of scientists at the Stanford Linear Accelerator Center, or SLAC for short, in conjunction with MIT, performed scattering experiments similar in principle to what Rutherford did to probe the atom 58 years earlier. Rutherford's target was a gold foil. In the SLAC experiment, the target was liquid hydrogen at a very cold temperature to keep the protons as close together as possible. As a source, Rutherford used a small piece of radium. The energy of the naturally occurring alpha particles was 7.7 million electron volts. Here we use electrons and accelerate them to nearly the speed of light. To do that, we construct a glass tube. Then we connect a negative charge to the entrance and a positive charge to the exit. When the battery is turned off, electrons flow in any direction. But with the battery turned on, the electrons accelerate down the tube along the electric field. To get a really high velocity, we connect more and more of these tubes together. At SLAC, the length of the tube is 3 kilometers. This creates electrons with 40,000 times the energy than the alpha particles used by Rutherford. The scintillator screen used by Rutherford covered the inside of the apparatus. He had to manually note the flash locations as he viewed them through the swiveling microscope. At SLAC, we partitioned the scintillator screen into small strips. Each strip has an attached photo element that converts the flash into an electrical signal. This enables the sending of electronic location coordinates to a computer. This is called a hodoscope. With this, we can precisely measure the scattering angles as the high-energy electrons penetrate the hydrogen atom and approach the proton at the center. SLAC also introduces a strong magnetic field that will cause the scattered electrons to curve as they pass through. As you'll recall from mass spectrometer and bubble chamber analysis techniques, the measured curvature will give us the momentum and velocity of the electrons. To measure this, a second hodoscope is installed at an angle. At the end of the process, the electrons enter a calorimeter that will measure its energy, much like we just did to discover the neutrino. Putting all these pieces together gives us the complete linear accelerator detector. It weighs 750 tons. If an electron's energy is large enough, making its de Broglie wavelength small enough, it can penetrate the proton. If the proton has no internal structure that would impact the penetrating electron, only a small amount of momentum would be lost by the electron. This is called elastic scattering. The key to graphing this is the concept of cross-section. If we take a look at the total area we are shooting into and the smaller area that represents the target, we see that the probability of a hit is equal to the target size divided by the total area. You can see that as the target cross-section shrinks, the probability of a hit goes down. Of course, we have a large number of targets in the area, the liquid hydrogen protons, so we add them together to get the total cross-section. It's interesting to note that if the probabilities are measured, the same equation gives us the target's cross-section size. For elastic scattering, the graph of interaction probability against the momentum transfer to the proton would look like this. The closer to the target we get, the smaller the cross-section gets, decreasing the probability of a hit, while at the same time the momentum transfer increases. For inelastic scattering, the proton takes a considerable amount of energy from the electron without materially changing the probability of a hit. This happens when there are internal components for the electron to excite and bounce off of. Here is what the SLAC MIT experiment found. It shows that the proton has parts. 3 parts. Back in 1964, a quark model was proposed by Murray Gell-Mann and George Zweig to help explain the wide variety of newly discovered heavy particles like the pion, kaon, and others. This discovery at SLAC in 1969 constituted evidence that quarks were real. We call particles made of quarks hadrons, meaning heavy. And in studying hadrons, we find 2 kinds. Those with 2 quarks are called mesons, and those with 3 quarks are called baryons. We have now seen 2 of each. There are 2 flavors of quarks that make up the proton and the neutron, called up quarks and down quarks. The up quark has a positive charge that is 2/3 the charge of an electron, with a spin of plus 1/2. The down quark has a negative charge that is 1/3 the charge of an electron, with a spin of minus 1/2. It also has a little more mass than the up quark. A proton contains 2 up quarks and 1 down quark, making its total charge positive and equal to the charge of an electron, with a spin of 1/2. A neutron contains 1 up quark and 2 down quarks, making its total charge equal to 0, with a spin of 1/2. This also gives the neutron a little more mass than the proton. The pion has 2, an up quark and an anti-down quark. The kaon also has 2, one of which is a third kind of quark called the strange quark. So these two are mesons. In addition to the up, down, and strange quarks, we have discovered the charm, top, and bottom quarks, for a total of 6. One of the key rules seems to be that they can combine in any combination of 2 or 3, as long as the sum total of charge always equals the charge of an electron or a proton, or 0. Armed with quarks, physicists intensified their search for some of the 3 quark particles predicted by Gilman and Zweig's theory. In 1947, the lambda particle was discovered. Here we see a V-shape with the creation of a pion and a proton. It was the proton that told us the decaying neutral particle, lambda, must have had 3 quarks. The particle was expected to live for about 10 to the minus 23 seconds, but actually survived for 10 to the minus 10 seconds. The property that caused it to live so long was dubbed strangeness and led to the discovery of the strange quark. In 1964, the Xi baryon was discovered at the Brookhaven National Laboratory. Antiprotons arrive from the left. One of these antiprotons collides with a hydrogen nucleus, a proton, resulting in mutual annihilation. The mass of the proton and the mass plus kinetic energy of the antiproton give birth to 2 heavy particles, a negative Xi and its antiparticle. Also in 1964, at the Brookhaven National Laboratory, the omega particle was discovered. This is one of the most famous bubble chamber pictures of all. It shows the discovery of this long-predicted particle. In this photograph, we have manufactured kaons entering the chamber on the left. To help see the omega particle, I'll remove all but the tracks associated with the omega event and work backwards from the V on the right that creates a pion and a proton. This is the trademark decay signature for the lambda particle. We also see V's in the upper right and in the lower middle where positron and electron pairs are created. This is the signature for high-energy gamma rays. If we draw lines back to where the lambda particle and the 2 gamma rays cross, we see that a neutral particle decayed into the neutral lambda and the 2 gamma rays. This is the decay signature for the neutral Psi particle. We can now draw the path of the Psi particle back to the kink, where another particle was decayed into the neutral Psi and a pion. Given all the masses, energies, strangeness, and charges involved, this fit the expected properties of the omega particle that's made up of 3 strange quarks. Tracing the path of the omega particle back to the kink in the path of the kaon, we can see the decay that created the omega particle and measure the length of time the omega particle existed. It has a very short life of 82 trillionths of a second. The physicist working on analyzing this photograph was so excited about his find that he woke up the director of the Brookhaven Laboratory in the middle of the night to give him the news. As with other predictions of previously unobserved particles, this discovery gave a tremendous boost to quark theory. Now's a good time to review the particle sizes we've seen so far. In our first segment, we used an electron microscope to see a carbon atom with a diameter of 0.14 nanometers. That's 1,000,000 times smaller than the width of a human hair. In our second segment, we probed the atom with alpha particles and found that the nucleus was very small compared to the atom. Here we have the carbon nucleus at around 26,000 times smaller than the carbon atom. The simplest nucleus is hydrogen's. It's just a proton. Its diameter is 78,000 times smaller than the carbon atom. In this segment, we probed the proton with high-velocity electrons and found that it had 3 components called quarks. Powerful accelerators and hadron colliders have put the upper limit on the diameter of the cross-section of quarks at 1 × 10⁻18 meters. That's 1,760 times smaller than a proton and 140 million times smaller than a carbon atom. This is also the upper limit for the cross-section of an electron. The neutrino is the smallest elementary particle, with a cross-section that is 1,000 times smaller than an electron or a quark. That makes it 140,000 trillion times smaller than the diameter of a human hair. When confronted with a vast number of observations, a first step to understanding is categorization. We try to find the similarities and differences between things. When it comes to elementary particles, we have already made some distinctions. We have the small light particles, like the electron and the neutrino, called leptons. And we have the quarks that make up the heavy particles, like protons and neutrons, called hadrons. Everything we see around us is made of these 3 stable elementary particles: the electron, the up quark, and the down quark. In addition to the proton and the neutron, we also found a number of other hadrons in this segment. There are many more, but only the proton is stable. A lone neutron's half-life is around 15 minutes. All the others are very unstable, and we only see them in collisions in the lab or on mountaintops. A particle's spin is another key distinction that helps us categorize all these particles. You'll recall that electrons have spin 1/2 and follow Pauli's exclusion principle. Photons have spin 1 and do not follow the exclusion principle. The statistics that describe spin 1/2 particle behavior in large groups was developed by Enrico Fermi and Paul Dirac. They are called fermions, after Mr. Fermi. The statistics that describe spin 1 particle behavior in large groups was developed by Satyendranath Bose and Albert Einstein. They are called bosons, after Mr. Bose. You can imagine that large groups of particles that can't fit into the same quantum state will behave differently than particles that can. In an energy well, the bosons all sit in a condensate at the bottom. The fermions arrange themselves in a hierarchy, like electrons in an atom. For example, a beam of photons can be made to have the same quantum state. This is how a laser works. On the other hand, the inability of electrons to fit into the same quantum state creates an outward pressure that halts a star's collapse and creates white dwarfs. In this segment, we also covered the muon. Another electron-like particle, called the tau, was discovered in 1975. Its mass is 3,484 times the mass of an electron, but we still call it a lepton. When these leptons decayed, their neutrinos were slightly different. So we have 2 additional neutrinos, the muon neutrino and the tau neutrino, to go along with the ubiquitous electron neutrino. So here we see the beginnings of the standard model of particle physics. We'll finish developing this model in our final segment on the Higgs boson.